about multiplicative kernels from Bessel to Calabi-Yau, Buchstaber and Kontsevich. Please go ahead.
First of all, I'm really very grateful to organizers to give me this possibility to be here and to speak here. My special thanks to Martina, who had helped me to overcome my stupid idiosyncrasy to bureaucratic paperwork and made my visit really possible. And the second thing which I want to do, I want to apologize for not only non-using the name of Cartan, but also non-using the notion of Cartan geometry in my talk. But I have a probably serious excuse. The subject which I want very superficially and very quickly, because it's absolutely stupid to try to explain all things in 40 minutes. The subject is so beautiful and so, I would say, inspiring. So I apply to young people, seriously think about the subject which became hot maybe 250, maybe 300 years ago, but it is still hot. So the object of my study, so-called multiplication kernels. So it's the kernel of this integral expression, k, big psi, the family of functions which with a spectrum or some other nature parameter lambda. And if you have the product of this function into different points, then multiplication kernel provides you possibility to express it in this integral form. You can have a little bit more fantasy to think about it like about some kind of associative multiplication with some structure constant in some algebra which lies behind this psi. Sometimes it is possible even to make more explicit. The second object, so-called Buchstaber polynomials. I forgot to say, I'm sorry, it's my nice obligation to say that all things which I will tell you, they are based on two works in progress. The first with Ilya Gayur from Toronto University and Duka van Straten from Mainz University. And second work in progress, almost finished paper with Viktor Buchstaber from Moscow, Steklov Institute, and Ilya Gayur from Toronto. So the second object is a family of polynomials, which I call Buchstaber polynomials, because it was Buchstaber who introduced this family, maybe in 1990, in some special, with some special aims. Maybe I will have time more to say about it. This family of polynomial depends on three variables x, y, z. Here I wrote it to save place like a function of elementary symmetric functions in x, y, z. Everybody knows what means sigma 1, sigma 2, and sigma 3. It means sum of x, pairwise product, sum of pairwise product, and the cubic x, y, z for sigma 3. So, and also three number parameter, real or complex, a1, a2, a3. So this family of polynomials, Buchstaber used to define so-called elliptic formal two-valued group law, which appeared in algebraic topology in study of spectrum of usual cohomology, of quantum cohomology, and elliptic cohomology. And third object of my interest today is the generalization of so-called Kontsevich polynomials. Kontsevich polynomials, formally speaking, it is just also polynomials which are also symmetric in x, y, z. So it can be expressed in terms of sigma 1, sigma 2, sigma 3, also with three parameters a, b, c, but the appearance of these polynomials is absolutely different. First of all, it is the discriminant. It is the discriminant of quadratic polynomial in T with the coefficients a plus sigma 1, sigma 2 minus b, sigma 3 plus c. I want to say why it is generalized, because Kontsevich used in his definition only special values of a, b, and c. For example, c for Kontsevich is always 0, and instead of a and b, he used some parameter t and function of this parameter. So it's some parameter lambda, because t I am using here. So for this special value of polynomials, Kontsevich introduced this polynomial in a description of so-called Hecke operators or in Langland's program over finite field. I absolutely have no time to discuss it, but I can maybe, if I will have small minute, I will try to explain how these polynomials really.
Volodya, coming back to the kernel, so what is the lambda there, and what's known, and what's the definition? So
I will give in my examples all this,
good.
because lambda it is a parameter, and the cycle of integration or this it is just very often it is just a residual integral. Very often it's a Cauchy type integral. So connection between this object graphically may be expressed in this form. So these generalized Kontsevich polynomials in one vertex, Buchstaber polynomials in this vertex. There is a third vertex, because both of them, they are so-called discriminantly splitted. What does it mean? It means that these polynomials, because they are symmetric, they can be, and in spite of that, Buchstaber polynomials has total degree 6, and Kontsevich polynomial has total degree 4. But if you consider them like a function of one of these variables x, y of z, you can write it in quadratic form. So you can consider another type of discriminant not by this parameter t, which I showed you for Kontsevich polynomial, but also for all of these variables x, y, z. I will show you. And then you obtain discriminant. And this discriminant is splitted. It means that it is written like it's factorized like a product of two absolutely identical polynomials of degree 3. And such type of splitness plays a very important role. I have also no time to say it, but in this audience it is important to make some kind of publicity. Discriminant polynomials, they play very discriminantly splitted polynomials. They are very often serve like spectral curves for models related to Kovalevska type top. So these three vertices, they are vertices of these polynomials. And there are two common points. One point, it is so-called generalized shift operator. Generalized shift operators, it is a beautiful class of operators. Initially, they were introduced by Delsart in 30s of 20th century. Of course, people knew about this, but they didn't know that they use generalized shift operators before Delsart. Delsart was the first to understand the importance of this notion in general. And then the full theory of such operators and even a group property of such operators, first, second, and third Lie theorem for them, were proven by Soviet mathematician Boris Levitan in his classical book, Generalized Shift Operators. And these operators, being, like I told you, a kind of generalized group, sometimes such groups people call hyper groups, they were a prototype of what people now call quantum groups, and it was also this notion was also in algebra was used in Ukraine by two mathematicians, Grigory Katz, not Victor Katz, Grigory Katz, and Palyutkin. And finally, there is another vertex. It's so-called two-valued groups. You remember that I told you that Buchstaber polynomial appeared like some condition to define the structure of formal two-valued group in algebraic topology in studying of spectrum. But it's happened that there is a relation with Kontsevich polynomial. And beauty of this is that Kontsevich polynomials, it is absolutely appeared in quite different situation. But there is some kind of hidden vertex, which you can always have in mind when you hear what I'm telling about. This vertex is an operation, addition law, or multiplication law. So there is a kind of formal group law, or addition or multiplication. And of course, there is a beautiful geometry. Moreover, now I will show you the absolutely fantastic formula which was discovered in 1828 by German mathematician Clausen. He wrote a paper in Krell journal, and the title of the paper just was this identity. This identity for so-called Gauss hypergeometric function, and this formula called Clausen duplication formula. So this hypergeometric function of type 2,1 in square can be written like a series given by hypergeometric function of type 3,2 with parameters explicitly expressed in terms of parameter of initial function. This duplication formula now are very, very popular among people who study number theory. Maybe it will be clear why. And there is a very, very deep and unusual partial case of this formula, which was proven by Swiss mathematician Schläfli in 19th century. And Schläfli proved it for so-called confluent hypergeometric functions. It is a tricky degeneration of Gauss hypergeometric function. And here I wrote this in the form, in the beautiful geometric form, which belongs to probably to Delsart in some non-geometric way. But this beautiful form I knew from classical book of Naum Vilenkin about representation, group representation and special functions. It's a fantastic book. I recommend you to read. It's full of ideas about representation of motion group, rotation group, and the relations with beautiful classical formulas for special functions. So here you have product of two confluent, it means degenerated hypergeometric function of type 0, 1 with parameters n over 2 and the variable x also multiplied by a over 2 in 2 points x and y. And then it can be expressed in terms of integral over n minus one-dimensional sphere of such type, of the same type of the function, taking, sorry, it's a mistake, it's not m, it's n. It's my misprint, it's n. And the variables x and y replaced by this expression. This expression is, it's a hidden form of cosine theorem for triangle. X and y, variables x and y, in fact, if you consider the functions in n-dimensional Euclidean space invariant with respect to the group or rotation or orthogonal group of n, then these functions invariant with respect to rotation, they form a homogeneous commutative coalgebra. So it's a coproduct in this commutative function algebra. For n equal 2, this commutative homogeneous coalgebra gives two-valued cyclic formal group. And there is an explicit link between this degenerate confluent hypergeometry and so-called zero-kind Bessel functions. For product of this formula gives you integral representation, which was discovered, of course, not in geometric form like this, in 19th century by mathematicians Gegenbauer and Sonin independently. And the product of these Bessel functions of zero kind you can express in such integral form with the Bessel function of zero kind in the third point z. The measure is z dz, but this expression can be written in very, very nice polynomial form. This polynomial S, it is exactly what people call now Kontsevich polynomial. Because if we construct what I told you, discriminant form of polynomial related to special cubic, and this special cubic f of t depends on one parameter a and free term equal to 0, this equation for eigenvalues psi usually called small a priori of the equation, because it also can be written in recursive form, and the corresponding recursive numbers, they are related to a priori numbers which was used a priori used in demonstration of irrationality of zeta function values in integer point. So this is why it is very important in number theory, for example. And eigenfunctions which solve this equation, they satisfy similar to Sonin-Gegenbauer formula with the polynomial p instead of s. And this polynomial p is exactly Kontsevich polynomial, which Kontsevich introduced in completely different situation related to number of computation number of Hecke operators. So this, you can ask what the polynomial is. I will show you. Polynomial I will show you later. It's absolutely beautiful geometric polynomial. And then it will be clear why this is a kind of cosine theorem, because this function s has geometric meaning of some square of triangle with x, y, and z, like a length of the beds. Okay, but of course I told you only part of the story, the classical part, which may be even not so inspiring. What is a modern part of the story? The modern part of the story that there are some differential equations which, given by differential operators, so-called Calabi-Yau differential operators, which are very important in mirror symmetry. There are generalization of classical Abel addition or multiplication theorem, and of course there are some links between this object and polynomials of Kontsevich and Buchstaber, which I told you. Moreover, there are interesting links with analytic Lagrange and analytic Hecke operators. It means that we can forget about finite fields. We can go to C to complex or to real field. And then the Lang-Lenz program can be extended in real or in complex world with explicit description of corresponding algebra. This algebra will be a kind of L2 algebra of temperate distributions. In this L2, you can write explicitly operators, scalar product, trace, Schmidt, everything, and all this can be generalized from finite fields, and corresponding Kontsevich polynomials will serve again, and even some more general Kontsevich polynomial will serve to describe these Hecke operators in C. And also, I have some personal reason to start to study this, and this personal reason it was my old theorem with Benjamin Enriquez from Duke in 2002, where we proved separation of variables for so-called Bavil-Mukai algebraic Lagrangian fibrations. So it is algebraic integrable systems which can be in some sense written in separate coordinates, and this representation gave a straightforward way to quantize this Bavil-Mukai fibration. Kontsevich in 2011 called me and said, Volodya, probably your theorem with Enriquez might be used to clarify something about these polynomials and with this motivic equation which was appeared in his paper over finite fields. And indeed, if you use multi-variable generalization of Abel theorem, which I hope to have time to mention, then you can go to our construction with Benjamin. Okay, literature. The story, if you are interested in the story of analytic Lang-Lenz and Hecke operators, there is a paper of Ettinghoff, Frenkel, and Kazhdan. The full ideology, which goes back to Clausen and non-Abelian theorem ideology, appeared in our paper with Vasily Golyshev, Anton Melit, and Dukov and Stratton. Just many interesting formulas and geometric meaning of multiplication kernels in terms of category of special Lagrangian submanifolds in the Weinstein category. It is in the paper of Kontsevich and Odesky. Then these two papers are in progress, which I have mentioned. One paper relates so-called Bessel kernels and geometry, combinatorics, and number theory behind all these Bessel kernels. I will have maybe 10, maybe 5 minutes to say about it. And also the second paper about discriminantly splitted polynomials, how they relate to integrable systems, how they relate to valued Buchstaber groups, and how they relate to Kontsevich multiplication formalism. This, that's what I hope briefly and superficially to tell you today. I will speak about mirror symmetry and Calabi-Yau, maybe about non-abelian Abel theorem, and how to relate Kontsevich and Buchstaber polynomials. Probably you have in mind that one of the main results that there is a kind of correspondence, and this birational correspondence establishes that any Kontsevich polynomial can be rewritten as Buchstaber polynomial and vice versa by birational transformation in three, in some sense, like special Krimono transformation. Okay, first, mirror symmetry and Calabi-Yau. What are these Calabi-Yau differential operators? It is just I will give a formal definition. So you have monic differential operators with polynomial coefficients. Each polynomial has degree which corresponds to its index, and the variable theta, it is a logarithmic derivation. So theta, it means not d over dt, but t d over dt. It's sometimes much more simply to write such operators and corresponding equations with respect to theta. So this polynomial operator in theta, and the origin, it's a point with so-called maximally unipotent monodromy. Why these operators are important? Let's suppose that we have a so-called Calabi-Yau manifold. It's manifold with trivial first chance class, with trivial anticanonical bundle, and we take a family which depends on parameter t. This parameter t, it's a parameter which lives on P1, on sphere. And of course, Calabi-Yau has this n0, if it is Calabi-Yau manifold of dimension n, so it has n0 form omega t up to holomorphic differential form, and then we have a family of such form for each mt. Then the standard theory, which is called Gauss-Manin connection, gives you so-called period function. Period function, it is integral of omega t over some certain cycle over your Calabi-Yau variety. And so the differential equation which has this function f as a solution, people call Picard-Fuchs equation. What's the example? So first of all, what is a mum point? Because for me, mum point is very important condition, because I can use it to write in proper way the basis in solution space of my corresponding differential equation. So if I have such differential operator with singular point at origin, then the origin, it's a maximally unipotent monodromy point. If the monodromy in this point can be written in such triangular form, with the diagonal elements 1, then 1 over 2, then 1 over 3 factorial. So this is coefficients of exponential series up to size of the monodromy matrix. So this form provides the following very nice property of so-called Frobenius base for solution space. All solutions of the differential equation with these differential operators can be written as a combination of some functions f sub k minus g for each g with coefficients which are degree of logarithm, such that the first, which corresponds to g equal to 0, it means that phi sub 0, phi node, which is also in this notation f node, it is just holomorphic or solution. And it can be written as a polynomial in T. Other solutions, of course, other coefficients, they are also polynomials, but they start not with 1, they start with T. And other solutions, phi 1, phi 2, they contain also logarithmic terms. So if we have such definitions, then we now have examples of this differential Calabi-Yau equation. So if my Calabi-Yau is one-dimensional, it means that it is just elliptic curve, because this is the simplest Calabi-Yau in dimension 1. So we have a family of elliptic curves. In this Legendrian form, my parameter t, it's just this t in Legendre form, then the period, one can check that integral of this form dx over y from 1 to infinity satisfy to the following differential equation, which has, of course, singularity for t equal 1 and for typically for this signs, I use this notation theta instead of d over dt. For n equal 2, Calabi-Yau, it will be so-called K3 surface. And then it is two-dimensional, complex two-dimensional variety. Typical example, it's a quartic. And this quartic, usually people call, if there is no this term, then this quartic is just Fermat quartic. But if we have this term, people call it dwarf quartic. So it's a dwarf form. And corresponding Picard-Fuchs for, so, you know, there are also, here you have integration by, of course, by lattice, which correspond to this torus behind of elliptic curve. In Calabi-Yau, in dimension 2, you also have some lattice more complicated, because the space of moduli space of K3, it has dimension 21, 19 plus 2. So you can have more complicated lattice, and you have more complicated integrals of period. They satisfy to this equation, which has degree 4, because you have this product of theta 4 times. So it's a very famous Picard-Fuchs for dwarf quartic. For n equal to 3, we have Calabi-Yau threefold with the Hodge numbers h to 1 equal to 1, and then Picard-Fuchs also has degree 4, and it looks like this Picard-Fuchs for dwarf in dimension 2, but with different coefficients. So it is also well-known differential equation. Now, how it relates to mirror symmetry. Of course, behind of this, first of all, was the physical great discovery. This discovery was published in '91 by Philippe Candelas, his wife Xenia de la Ossa from Oxford, and also by two collaborators, Phil Green and Larry Parks. They introduced for this dwarf differential Picard-Fuchs operator, they introduced explicit observation. If we write now these Frobenius solutions in 0, it is mum point. So we can write analytic solution, and this analytic solution, fantastically, it is hypergeometric type. You can write it, and you see that all coefficients, like I promised you, start with 1, and all coefficients are, I didn't promise you that they will be integer. I just wrote that they C, but it happened that they were integer. Okay, they said, and then they consider phi 1, which contains this logarithmic term, no more analytic solution. Okay, they wrote this solution, and it's happened that it is also formal series in T, but no more integrality. It is only rational. Then Liang and Xingtun-Yao in '96, it's 5 years later, they saved the situation, and they introduced so-called mirror coordinate, Q of T, which is exponential of ratio phi 1 and phi 0. If you write it in logarithmic form, it is just T of exponential of f. You remember that this phi can be rewrite as a combination of f. And then this exponential series all again have integer coefficient, some miraculous observation. They call this so-called canonical or mirror coordinate. This integer coefficient series starts with t, and it means that you can invert it. And then you have expression of t in function of q. And again, this expression, of course, has only rational coefficients. Okay, then we write this basis, Frobenius basis. Then we have this ratio. Then we have this series in Q, and we can consider the second order operator over Q. So it's a theta, our theta in Q coordinates, in mirror coordinates, applying to this ratio phi 2, phi 0. So this is, I'm sorry, it's phi 1, you remember it was log Q. And phi 2, phi 0, it's the first term with logarithm in square. And then, again, you have integral coefficients. And this expression with integral coefficients, this theta in Q of phi 2, phi 0, physicists call Yukawa coupling. So you have a series with integer coefficients with respect to Q, and you can rewrite this Yukawa coupling with integer coefficients in Q like a series not in Q, but in a rational expression Q to K, 1 minus Q to K. It is so-called Lambert series representation. And then you have integer coefficients in these representations, which are n sub k, and always common coefficients k to 3. 1 over 5, it is a common factor. These coefficients n, k, 5, 2008, 175, etc., physicists call instanton numbers. I have no comments about it, how they relate to real instanton, but it is typical argo in this mirror science. And then,
I know that you have been discussing with Henrik that he will let you know 5 minutes. He made considerable effort.
2 minutes, okay. Okay. So I told you only the story which we didn't do, because I told you old story. Our story that we did, we just have 2 minutes, and I will show you our results. We have the same results for more simple but more exciting equation. Not this Calabi-Yau. We call this our equation quasi-Calabi-Yau because it is not always with so-called Mum point. And this equation, it is a degree of Bessel equation. So I want to say that there is a link why it was so beautiful, because this I can't hide that these instanton numbers, they are nothing but so-called Gromov-Witten invariants, and it is the main result of 1990s. It's a Giventhal and Liang-Liu-Yau independent theorem that instanton numbers coincide with so-called Gromov-Witten invariants. It means it is number of degree k rational curves, nk, it's a number of degree k rational curves which lie on our 5-degree Calabi-Yau threefold. We have the similar result for, it means that I should stop.
Turn off the alarm and take 1.5 more minutes.
Yeah, one minute I will show you. This is just a reminder about addition laws, which I mentioned. And this addition laws you can use to generalize Abel theorem. And this Abel theorem gives you multi-variable analog of kernel multiplication. You can write it for n equal to one like my multiplication kernel. This Odesky and Kontsevich observed that sometimes you can really express this integral expression like associative algebra, infinite associative algebra structure. And this is a classical Sonin-Gegenbauer formula. This degree 4 polynomial, it's my S of x, my area of triangle. Why it is area? Because this quartic can be factorized in Heron configuration. This is my Bessel. I will show you just beautiful picture. This is again Sonin Gegenbauer proof. Oh, this is my this is my triangle, and if you write this instead of degree 4, you can make substitution u square, v square, w square. This conic will become quartic, and this in terms of u, v, and w, it's factorized. One of our main results with Duca and Ilya that it is always true, not only for Bessel, for Bessel 2, but for Bessel n. And this is a beautiful result. Why it is beautiful result? Because it's difficult to prove that it is always factorized like this or over lattice with square root of unity, but also each polynomial which is factorized in this form gives you n-valued multiplication law of Buchstaber and Ries. That's absolutely unexpected consequence of this. Thank you very much. Next time I will finish.
So, one question maybe? Anyone? Okay, no questions, no comments?
No.
Then let us thank the speaker again.